All right, so this is section 5.3, part 3, and we're going to do some examples or some application problems in this part. So given a marginal cost function, to find the total cost of producing, say, units 100 to 400, we could proceed as follows. Integrate the marginal cost to find the total cost, evaluate at 400 to find the total cost up to 400, or unit 400, and then subtract the evaluation at 100 to leave just the cost of units 100 to 400. Therefore, the cost of a succession of units is equal to the definite integral of the marginal cost function. Okay? So to find total cost, we integrate that marginal cost function and evaluate from whatever units we need to. So let's try an example. It says a company's marginal cost function is MC of x equals 75 over square root of x, where x is the number of units. We need to find the total cost of producing units 100 to 400. All right, so we have a marginal cost, and in order to find total cost, we have to take an integral. So we're going to integrate from 100 to 400. We're going to integrate 75 x to the negative 1/2. As you're rewriting this function into your integral, make sure that you take the time to switch your function over to rational exponents and putting all your variables in the numerator so it's an easier function to take the integral of. So when we integrate this, we end up with 75 times, we do negative 1/2 plus 1, which is 1/2. And 1 over 1/2 is 2. So we have 2x to the positive 1/2. And we're going to integrate that from 100 to 400. So if we simplify 75 times 2, I've got 150 x to the 1/2 evaluated from 100 to 400. So when we plug our numbers in, 150 times 400 to the 1/2 power minus 150 times 100 to the 1/2 power. You can calculate this by hand or plug it straight into your calculator. Wouldn't matter either way. But you get 1,500. And what that means is the cost of producing units 100 to 400 is $1,500. All right. So this works not just for marginal cost, but it works for finding any total accumulation. So integrating any rate from A to B gives a total accumulation at that rate between A to B. Okay, so it doesn't work for just marginal cost, although that's a big one. It works for marginal cost. If you know the marginal cost, you can integrate from A to B, and that would give you the total units from A to B. If you know what the productivity rate is, again, you can integrate. That would find the total work accomplished between so many hours. If you know the sales rate of a product, you can integrate that, giving you total sales from day A to day B. Okay? And again, in repetitive tasks, a person's productivity usually increases with practice until it is eventually slowed by monotony. So let's try another example. It says a technician can test computer chips at a rate of -3t squared plus 18t plus 15 chips per hour. And that works for hours between 0 and 6. Where t is the number of hours after 9 a.m. So that means at 9 a.m., that's times 0. And we need to figure out how many chips can be tested between 10 a.m. and 1 p.m. All right, so your 10 a.m. would be 1, because that's 1 hour after 9 a.m. And then your 1 p.m. would be 4, because it's 4 hours after 9 a.m. So we need to integrate from 1 to 4, the function negative 3t squared plus 18t plus 15 dt. All right, so I want you to pause the video, integrate this function, and come back and check your work. All right, so if you integrate, you end up with negative t cubed plus 9t squared plus 15t. I wrote out this middle step showing you work. If you can go straight from the integral to that simplified step, that's fine. You don't have to write out that middle step. But if it helps you, go ahead and write it out. It's not a big deal. Once you find the integral, we're going to plug in 4 and then subtract the evaluated function at 1. When you plug all of that in, you end up with 117. So that means between 10 a.m. and 1 p.m. that 117 chips can be tested. All right, let's keep going. All right, so the symbol sigma, which is the Greek letter S, is used in mathematics to indicate a sum. So the Riemann sum can be written as sigma from 1 to n f of x sub k delta x. The fact that the Riemann sum approaches the definite integral could be expressed as follows. Sigma 1 to n f of x sub k times dx approaches the integral from a to b f of x dx. Okay? Or sigma becomes integral and delta becomes d as n is going to infinity. Those little rectangles under the curve. That is, the integration notation reminds us that the definite integral represents a sum of rectangles of height f of x and width d of x. Okay? Riemann sums can be calculated for any continuous function, not just negative functions. The following diagram illustrates a Riemann sum for a continuous function that takes positive and negative values. Everything we did so far was positive functions only. But it can be used to figure out the area under the curve if you have a function that's both positive and negative. So what you would do is take your function and break it into two parts. So I've got let me use a different color. This first part from a until my function hits 0, so that x sub 4 value. And then I can segment it from that x sub 4 value till when x is equal to b. And what we would end up doing is finding the integral of the function from a to x sub 4, whatever this middle value is, and then subtracting off the negative part of the function. So we'd find the integral again, starting at that x sub 4 value, whatever that value is, and going to b of the function. So we're still finding integrals, but we're just going to take and find the integral for the positive part of the function and then subtract off the negative part of the function. All right, and that's what this next value says. By taking the limit, the definite integral, where the function lies below the x-axis, will give the negative area of the curve between the curve and that x-axis. Therefore, the definite integral of such a function from a to b will give the signed areas between the curves. We've got the positive part, which they're calling a up, and then we have the negative part, which they're calling a down. Okay, and so the entire integral is, if we say the integral from a to b of this function is going to be the positive area, or that a up, minus area down. And again, it's what we were talking about on the last slide. we're going to break this function up. So there's some, we'll call it C value here, to where I'm going to find the integral from a to c of the function. And then I'm going to subtract off from c to b that area that's below the x-axis. And then you would have the integral, or the area under the curve, for that function. All right, that's the end of section 5.3.